Infrared is invisible radiant energy, electromagnetic radiation with longer wavelengths than those of visible light, extending from the nominal red edge of the visible spectrum at 700 nanometers to 1 ohm. Most of the thermal radiation emitted by objects near room temperature is infrared. Infrared radiation was discovered in 1800 by astronomer William Herschel, who discovered a type of invisible radiation in the spectrum beyond red light, by means of its effect upon a thermometer. Slightly more than half of the total energy from the Sun was eventually found to arrive on Earth in the form of infrared. The balance between absorbed and emitted infrared radiation has a critical effect on Earth's climate. Infrared energy is emitted or absorbed by molecules when they change their rotational vibrational movements. Infrared energy elicits vibrational modes in a molecule through a change in the dipole moment, making it a useful frequency range for study of these energy states for molecules of the proper symmetry. Infrared spectroscopy examines absorption and transmission of photons in the infrared energy range. Infrared radiation is used in industrial, scientific, and medical applications. Night vision devices using active near-infrared illumination allow people or animals to be observed without the observer being detected. Infrared astronomy uses sensor-equipped telescopes to penetrate dusty regions of space, such as molecular clouds, detect objects such as planets, and to view highly red-shifted objects from the early days of the universe. Infrared thermal imaging cameras are used to detect heat loss in insulated systems, to observe changing blood flow in the skin, and to detect overheating of electrical apparatus. Thermal infrared imaging is used extensively for military and civilian purposes. Military applications include target acquisition, surveillance, night vision, homing and tracking. Humans at normal body temperature radiate chiefly at wavelengths around 10 Ai1/4 m. Non-military uses include thermal efficiency analysis, environmental monitoring, industrial facility inspections, remote temperature sensing, short-ranged wireless communication, spectroscopy, and weather forecasting. Definition and relationship to the electromagnetic spectrum. Infrared radiation extends from the nominal red edge of the visible spectrum at 700 nanometers to 1 ohm. This range of wavelengths corresponds to a frequency range of approximately 430 Hz down to 300 GHz. Below infrared is the microwave portion of the electromagnetic spectrum. Natural infrared, sunlight, at an effective temperature of 5780 kelvins, is composed of nearly thermal spectrum radiation that is slightly more than half infrared. At zenith, sunlight provides an irradiance of just over 1 kilowatt per square meter at sea level. Of this energy, 527 watts is infrared radiation, 445 watts is visible light, and 32 watts is ultraviolet radiation. On the surface of Earth, at far lower temperatures than the surface of the Sun, almost all thermal radiation consists of infrared in various wavelengths. Of these natural thermal radiation processes, only lightning and natural fires are hot enough to produce much visible energy, and fires produce far more infrared than visible light energy. Regions within the infrared. In general, objects emit infrared radiation across a spectrum of wavelengths, but sometimes only a limited region of the spectrum is of interest because sensors usually collect radiation only within a specific bandwidth. Thermal infrared radiation also has a maximum emission wavelength, which is inversely proportional to the absolute temperature of object, in accordance with Wien's displacement law. Therefore, the infrared band is often subdivided into smaller sections. Commonly used subdivision scheme. A commonly used subdivision scheme is an IR and SWIR is sometimes called reflected infrared, whereas MWIR and LWIR is sometimes referred to as thermal infrared. Due to the nature of the blackbody radiation curves, typical hot objects, such as exhaust pipes, often appear brighter in the MW compared to the same object viewed in the LW. CIE division scheme. The International Commission on Illumination recommended the division of infrared radiation into the following three bands: IRA, 700 nm Euro 1400 nm, IRB, 1400 nm Euro 3000 nm, IRC, 3000 nm Euro 1 ohm, ISO 20473 scheme, ISO 20473. Specifies the following scheme: Astronomy Division Scheme. Astronomers typically divide the infrared spectrum as follows. These divisions are not precise and can vary depending on the publication. The three regions are used for observation of different temperature ranges, and hence different environments in space. Sensor Response Division Scheme. A third scheme divides up the band based on the response of various detectors, near-infrared, from 0.7 to 1.0 AA micrometer. Short-wave infrared, 1.0 to 3 AA micrometer. In-gas covers to about 1.8 AA micrometer. The less sensitive lead salts cover this region. Mid-wave infrared, 3 to 5 AA micrometer. Long-wave infrared, 8 to 12, or 7 to 14 AA micrometer. Very long-wave infrared. Near-infrared is the region closest in wavelength to the radiation detectable by the human eye. Mid and far infrared are progressively further from the visible spectrum. Other definitions follow different physical mechanisms and the newest follow technical reasons. Unfortunately, international standards for these specifications are not currently available. The onset of infrared is defined at various values, typically between 700 nm and 800 nm, but the boundary between visible and infrared light is not precisely defined. The human eye is markedly less sensitive to light above 700 nm wavelength, so longer wavelengths make insignificant contributions to scenes illuminated by common light sources. However, particularly intense near-IR light can be detected up to approximately 780 nm, and will be perceived as red light. Sources providing wavelengths as long as 1050 nm can be seen as a dull red glow in intense sources, causing some difficulty in near-IR illumination of scenes in the dark. Leaves are particularly bright in the near-IR, and if all visible light leaks from around an IR filter are blocked, and the eye is given a moment to adjust to the extremely dim image coming through a visually opaque IR passing photographic filter, it is possible to see the wood effect that consists of IR glowing foliage. Telecommunication bands in the infrared. In optical communications, the part of the infrared spectrum that is used is divided into 7 bands based on availability of light sources transmitting absorbing materials and detectors. The C-band is the dominant band for long-distance telecommunication networks. The S and L bands are based on less well-established technology, and are not as widely deployed. Heat. Infrared radiation is popularly known as heat radiation, but light and electromagnetic waves of any frequency will heat surfaces that absorb them. Infrared light from the Sun accounts for 49% of the heating of Earth, with the rest being caused by visible light that is absorbed then re-radiated at longer wavelengths. Visible light or ultraviolet emitting lasers can char paper, and incandescently hot objects emit visible radiation. Objects at room temperature will emit radiation concentrated mostly in the 8 to 25 AA micrometer band, but this is not distinct from the emission of visible light by incandescent objects and ultraviolet by even hotter objects. Heat is energy in transit that flows due to temperature difference. Unlike heat transmitted by thermal conduction or thermal convection, thermal radiation can propagate through a vacuum. Thermal radiation is characterized by a particular spectrum of many wavelengths that is associated with emission from an object, due to the vibration of its molecules at a given temperature. Thermal radiation can be emitted from objects at any wavelength, and at very high temperatures such radiations are associated with spectra far above the infrared, extending into visible, ultraviolet, and even X-ray regions. Thus, the popular association of infrared radiation with thermal radiation is only a coincidence based on typical temperatures often found near the surface of planet Earth. The concept of emissivity is important in understanding the infrared emissions of objects. This is a property of a surface that describes how its thermal emissions deviate from the ideal of a black body. To further explain, two objects at the same physical temperature will not show the same infrared image if they have differing emissivities. Applications: night vision. Infrared is used in night vision equipment when there is insufficient visible light to see. Night vision devices operate through a process involving the conversion of ambient light photons into electrons that are then amplified by a chemical and electrical process and then converted back into visible light. Infrared light sources can be used to augment the available ambient light for conversion by night vision devices, increasing in the dark visibility without actually using a visible light source. The use of infrared light and night vision devices should not be confused with thermal imaging, which creates images based on differences in surface temperature by detecting infrared radiation that emanates from objects and their surrounding environment. Thermography. Infrared radiation can be used to remotely determine the temperature of objects. This is termed thermography, or in the case of very hot objects in the near or visible it is termed pyrometry. Thermography is mainly used in military and industrial applications, but the technology is reaching the public market in the form of infrared cameras on cars due to the massively reduced production costs. Thermographic cameras detect radiation in the infrared range of the electromagnetic spectrum and produce images of that radiation. Since infrared radiation is emitted by all objects based on their temperatures, according to the black-body radiation law, thermography makes it possible to see one's environment with or without visible illumination. The amount of radiation emitted by an object increases with temperature, therefore thermography allows one to see variations in temperature. Hyperspectral imaging. A hyperspectral image, a basis for chemical imaging, is a picture containing continuous spectrum through a wide spectral range. Hyperspectral imaging is gaining importance in the applied spectroscopy, particularly in the fields of NIR, SWIR, MWIR, and LWIR spectral regions. Typical applications include biological, mineralogical, defense, and industrial measurements. Thermal infrared hyperspectral camera can be applied similarly to a thermographic camera, with the fundamental difference that each pixel contains a full LWIR spectrum. Consequently, chemical identification of the object can be performed without a need for an external light source such as the sun or the moon. Such cameras are typically applied for geological measurements, outdoor surveillance and UAV applications. Other imaging. In infrared photography, infrared filters are used to capture the near-infrared spectrum. Digital cameras often use infrared blockers. Cheaper digital cameras and camera phones have less effective filters and can see intense near-infrared, appearing as a bright purple-white color. This is especially pronounced when taking pictures of subjects near IR bright areas, where the resulting infrared interference can wash out the image. There is also a technique called T-ray imaging, which is imaging using far infrared or terahertz radiation. Lack of bright sources can make terahertz photography more challenging than most other infrared imaging techniques. Recently T-ray imaging has been of considerable interest due to a number of new developments such as terahertz time-domain spectroscopy. Tracking. Infrared tracking, also known as infrared homing, refers to a passive missile guidance system, which uses the emission from a target of electromagnetic radiation in the infrared part of the spectrum to track it. Missiles that use infrared seeking are often referred to as heat seekers, since infrared is just below the visible spectrum of light in frequency and is radiated strongly by hot bodies. Many objects such as people, vehicle engines, and aircraft generate and retain heat, and as such, are especially visible in the infrared wavelengths of light compared to objects in the background. Heating. Infrared radiation can be used as a deliberate heating source. According to this Mayo Clinic article states that, several studies have looked at using infrared saunas in the treatment of chronic health problems, such as high blood pressure, congestive heart failure and rheumatoid arthritis, and found some evidence of benefit. For example, it is used in infrared saunas to heat the occupants, and also to remove ice from the wings of aircraft. Far infrared is also gaining popularity as a safe heat therapy method of natural health care and physiotherapy. Infrared can be used in cooking and heating food as it predominantly heats the opaque, absorbent objects, rather than the air around them. Infrared heating is also becoming more popular in industrial manufacturing processes, for example curing of coatings, forming of plastics, annealing, plastic welding, print drying. In these applications, Infrared heaters replace convection ovens and contact heating. Infrared heaters produce heat that is a product of invisible light, and they consist of three parts: infrared light bulbs, a heat exchanger, and a fan that blows air onto the exchanger to disperse the heat. Efficiency is achieved by matching the wavelength of the infrared heater to the absorption characteristics of the material. Communications. IR data transmission is also employed in short-range communication among computer peripherals and personal digital assistants. These devices usually conform to standards published by IRDA, the Infrared Data Association. Remote controls and IRDA devices use infrared light-emitting diodes to emit infrared radiation that is focused by a plastic lens into a narrow beam. The beam is modulated, that is switched on and off, to encode the data. The receiver uses a silicon photodiode to convert the infrared radiation to an electric current. It responds only to the rapidly pulsing signal created by the transmitter, and filters out slowly changing infrared radiation from ambient light. Infrared communications are useful for indoor use in areas of high population density. IR does not penetrate walls and so does not interfere with other devices in adjoining rooms. Infrared is the most common way for remote controls to command appliances. Infrared remote control protocols like RC5, SISE, are used to communicate with infrared. Free space optical communication using infrared lasers can be a relatively inexpensive way to install a communications link in an urban area operating at up to 4 gigabit/s, compared to the cost of burying fiber optic cable. Infrared lasers are used to provide the light for optical fiber communication systems. Infrared light with a wavelength around 1330 nm or 1550 nm are the best choices for standard silica fibers. IR data transmission of encoded audio versions of printed signs is being researched as an aid for visually impaired people through the RIAS project. Spectroscopy. Infrared vibrational spectroscopy is a technique that can be used to identify molecules by analysis of their constituent bonds. Each chemical bond in a molecule vibrates at a frequency characteristic of that bond. A group of atoms in a molecule may have multiple modes of oscillation caused by the stretching and bending motions of the group as a whole. If an oscillation leads to a change in dipole in the molecule, then it will absorb a photon that has the same frequency. The vibrational frequencies of most molecules correspond to the frequencies of infrared light. Typically, the technique is used to study organic compounds using light radiation from 4000 to 400 µ1, the mid-infrared. A spectrum of all the frequencies of absorption in a sample is recorded. This can be used to gain information about the sample composition in terms of chemical groups present and also its purity. Meteorology. Weather satellites equipped with scanning radiometers produce thermal or infrared images, which can then enable a trained analyst to determine cloud heights and types, to calculate land and surface water temperatures, and to locate ocean surface features. The scanning is typically in the range 10.3 to 12.5 AA micrometer. High, cold ice clouds such as cirrus or cumulonimbus show up bright white. Lower warmer clouds such as stratus or stratocumulus show up as gray with intermediate clouds shaded accordingly. Hot land surfaces will show up as dark gray or black. One disadvantage of infrared imagery is that low clouds such as stratus or fog can be a similar temperature to the surrounding land or sea surface and does not show up. However, using the difference in brightness of the IR4 channel and the near-infrared channel, low cloud can be distinguished, producing a fog satellite picture. The main advantage of infrared is that images can be produced at night, allowing a continuous sequence of weather to be studied. These infrared pictures can depict ocean eddies or vortices and map currents such as the Gulf Stream, which are valuable to the shipping industry. Fishermen and farmers are interested in knowing land and water temperatures to protect their crops against frost or increase their catch from the sea. Even El Niño plus or minus O phenomena can be spotted. Using color-digitized techniques, the gray-shaded thermal images can be converted to color for easier identification of desired information. The main water vapor channel at 6.40 to 7.08 AA micrometer can be imaged by some weather satellites and shows the amount of moisture in the atmosphere. Climatology. In the field of climatology, atmospheric infrared radiation is monitored to detect trends in the energy exchange between the Earth and the atmosphere. These trends provide information on long-term changes in Earth's climate. It is one of the primary parameters studied in research into global warming, together with solar radiation. A pyrgeometer is utilized in this field of research to perform continuous outdoor measurements. This is a broadband infrared radiometer with sensitivity for infrared radiation between approximately 4.5 AA micrometer and 50 AA micrometer. Astronomy. Astronomers observe objects in the infrared portion of the electromagnetic spectrum using optical components, including mirrors, lenses and solid-state digital detectors. For this reason it is classified as part of optical astronomy. To form an image, the components of an infrared telescope need to be carefully shielded from heat sources, and the detectors are chilled using liquid helium. The sensitivity of Earth-based infrared telescopes is significantly limited by water vapor in the atmosphere, which absorbs a portion of the infrared radiation arriving from space outside of selected atmospheric windows. This limitation can be partially alleviated by placing the telescope observatory at a high altitude, or by carrying the telescope aloft with a balloon or an aircraft. Space telescopes do not suffer from this handicap, and so outer space is considered the ideal location for infrared astronomy. The infrared portion of the spectrum has several useful benefits for astronomers. Cold, dark molecular clouds of gas and dust in our galaxy will glow with radiated heat as they are irradiated by embedded stars. Infrared can also be used to detect protostars before they begin to emit visible light. Stars emit a smaller portion of their energy in the infrared spectrum, so nearby cool objects such as planets can be more readily detected. Infrared light is also useful for observing the cores of active galaxies, which are often cloaked in gas and dust. Distant galaxies with a high redshift will have the peak portion of their spectrum shifted toward longer wavelengths, so they are more readily observed in the infrared. Art history. Infrared reflectography, or FRES, as called by art historians, are taken of paintings to reveal underlying layers, in particular the underdrawing or outline drawn by the artist as a guide. This often uses carbon black, which shows up well in reflectograms, as long as it has not also been used in the ground underlying the whole painting. Art historians are looking to see whether the visible layers of paint differ from the underdrawing or layers in between. Such alterations are called pentimenti when made by the original artist. This is very useful information in deciding whether a painting is the prime version by the original artist or a copy, and whether it has been altered by over-enthusiastic restoration work. In general, the more pentimenti the more likely a painting is to be the prime version. It also gives useful insights into working practices. Among many other changes in the Arnulfni portrait of 1434, the man's face was originally higher by about the height of his eye. The woman's was higher, and her eyes looked more to the front. Each of his feet was underdrawn in one position, painted in another, and then overpainted in a third. These alterations are seen in infrared reflectograms. Similar uses of infrared are made by historians on various types of objects, especially very old written documents such as the Dead Sea Scrolls, the Roman works in the Villa of the Papyri, and the Silk Road texts found in the Dunhuang caves. Carbon black used in ink can show up extremely well. Biological systems. The pit viper has a pair of infrared sensory pits on its head. There is uncertainty regarding the exact thermal sensitivity of this biological infrared detection system. Other organisms that have thermoreceptive organs are pythons, some boas, the common vampire bat, a variety of jewel beetles, darkly pigmented butterflies, and possibly blood-sucking bugs. Although near-infrared vision has long been deemed impossible due to noise in visual pigments, sensation of near-infrared light was reported in the common carp and in 3 cichlid species. Fish use NIR to capture prey and for phototactic swimming orientation. NIR sensation in fish may be relevant under poor lighting conditions during twilight and in turbid surface waters. Photobiomodulation, near-infrared light, or photobiomodulation, is used for treatment of chemotherapy-induced oral ulceration as well as wound healing. There is some work relating to anti-herpes virus treatment. Research projects include work on central nervous system healing effects via cytochrome C oxidase upregulation and other possible mechanisms. Health hazard: strong infrared radiation in certain industry high heat settings may be hazard to the eyes, resulting in damage or blindness to the user. Since the radiation is invisible, special IR-proof goggles must be worn in such places. Earth as an infrared emitter. Earth's surface and the clouds absorb visible and invisible radiation from the sun and re-emit much of the energy as infrared back to atmosphere. Certain substances in the atmosphere, chiefly cloud droplets and water vapor, but also carbon dioxide, methane, nitrous oxide, sulfur hexafluoride, and chlorofluorocarbons, absorb this infrared, and re-radiate it in all directions including back to Earth. Thus, the greenhouse effect keeps the atmosphere and surface much warmer than if the infrared absorbers were absent from the atmosphere. History of infrared science. The discovery of infrared radiation is ascribed to William Herschel, the astronomer, in the early 19th century. Herschel published his results in 1800 before the Royal Society of London. Herschel used a prism to refract light from the sun and detected the infrared, beyond the red part of the spectrum, through an increase in the temperature recorded on a thermometer. He was surprised at the result and called them calorific rays. The term infrared did not appear until late in the 19th century. Other important dates include 1737, a Permel Marly du Car Saint-Elliot predicted what is today known as infrared radiation in Dissertation sur la nature et la propagation du feu. 1835, Macedonio Melloni made the first thermopile IR detector. 1860, Gustav Kirchhoff formulated the blackbody theorem. 1873, Willoughby Smith discovered the photoconductivity of selenium. 1879, Stefan Boltzmann law formulated empirically that the power radiated by a blackbody is proportional to T4. 1880s and 1890s, Lord Rayleigh and Wilhelm Wien solved part of the blackbody equation, but both solutions diverged in parts of the electromagnetic spectrum. This problem was called the ultraviolet catastrophe and infrared catastrophe. 1901, Max Planck published the blackbody equation and theorem. He solved the problem by quantizing the allowable energy transitions. 1905, Albert Einstein developed the theory of the photoelectric effect. 1917, Theodore Case developed the Thales sulfide detector. British scientist built the first infrared search and track device able to detect aircraft at a range of 1 mile. 1935, lead salts early missile guidance in World War II. 1938, Total predicted that the pyroelectric effect could be used to detect infrared radiation. 1945, the Zieldre currency T1229 Vamper infrared weapon system was introduced as the first portable infrared device for military applications. 1952, H. Welker grew synthetic and SB crystals. 1950s, Paul Kruse and Texas Instruments recorded infrared images. 1950s and 1960s, nomenclature and radiometric units defined by Fred Nicodemus, G. J. Zissis and R. Clark. Robert Clark Jones defined D. 1958, W. D. Lawson discovered IR detection properties of HGCDTE. 1958, Falcon and Sidewinder missiles were developed using infrared technology. 1961, J. Cooper demonstrated pyroelectric detection. 1964, W. G. Evans discovered infrared thermoreceptors in a pyrophile beetle. 1965, first IR handbook. First commercial images, and Richards develops detection, recognition and identification modeling there. 1970, Willard Boyle and George E. Smith proposed CCD at Bell Labs for picture phone. 1972, Common Module Program started by NVESD. 1978, infrared imaging astronomy came of age, observatories planned, IATF on Mauna Kea opened. 32 by 32 and 64 by 64 arrays produced using NSB, HGCDTE and other materials. 2013, on February 14, researchers developed a neural implant that gives rats the ability to sense infrared light, which for the first time provides living creatures with new abilities, instead of simply replacing or augmenting existing abilities. See also. References. External links. Infrared, A Historical Perspective, Infrared Data Association, a standards organization for infrared data interconnection, SISC protocol, how to build an USB infrared receiver to control PCs remotely, infrared waves, detailed explanation of infrared light. Herschel's original paper from 1800 announcing the discovery of infrared light, the Thermographics Library, collection of thermogram.